All right, let's jump right in. Have you ever just stopped and wondered how things, well, how they stick together? I mean, everything from a single grain of salt to the DNA inside every one of your cells. There's this incredible, invisible glue holding our entire world together. Today, we're going to figure out what that glue is.
So, what holds everything together? It's one of the most fundamental questions you can ask. And the answer isn't as simple as, nails holding wood together or glue for paper. When you get down to the microscopic level, the forces that build our world are so much more elegant and way more powerful.
The secret, it turns out, lies in just a handful of different atomic bonds. These are all the different ways that atoms can connect with each other. Some of these bonds are unbelievably strong, kind of like a weld, while others are more like a gentle static cling. So let's break them down.
We're going to start with the heavy hitters. These are the primary bonds, the really strong, fundamental connections that form the backbone of pretty much every material you can imagine. First up, we have the ionic bond. Now, the best way to think about this one is as a complete and total handoff. You've got one atom that wants to get rid of an electron and another atom that desperately wants to take one. It's a perfect one-way deal. And the classic example here is table salt. You've got sodium, and it gives one of its electrons to chlorine. As soon as that happens, the sodium becomes positively charged, and the chlorine becomes negatively charged. And what do opposites do? They attract. They act like tiny little magnets, snapping together to form that hard crystal structure of salt. Okay, next up is the covalent bond. This is a completely different game plan. Instead of a handoff, this is all about sharing. Here, you have two atoms that both need an electron, so they agree to share a pair between them. It's a mutual arrangement that keeps them both stable and connected. A really great way to picture this is two people holding on tight to the same rope. Neither one is letting go. And this bond, this is the foundation of life itself. The incredibly complex molecules that make you who you are, your DNA, your proteins, they are all held together by these powerful covalent sharing bonds. But not all sharing is fair. Sometimes it's nonpolar, which is like a perfectly balanced, even tug of war. But other times it's polar, where one atom is a little more greedy. It's like a blanket hog, pulling those shared electrons closer to itself. And that creates a slight positive charge on one end and a slight negative charge on the other. Now, remember that idea because it's going to be important later. Our final heavy-duty bond is the metallic bond, and honestly, it's in a league of its own. Here, instead of atoms making one-on-one deals, all the metal atoms just kind of toss their outer electrons into a big community pot. It creates this shared sea of electrons that belongs to all the atoms at once. And this sea of electrons is really the secret to what makes metals, well, metals. Because those electrons can flow freely, metals are fantastic at conducting electricity. And because the atoms aren't locked into these super rigid positions, they can slide past one another. That's why you can bend a paperclip without it just snapping in half. Okay, so we've gone through the powerhouses, but beyond those primary bonds, there are these weaker, more subtle forces. And I'm telling you, do not let that word weaker fool you. Their collective impact is absolutely world-changing. So let's meet the hydrogen bond. Remember that unequal polar sharing we were just talking about, the blanket hog? Well, when a hydrogen atom is stuck in one of those unequal bonds, it ends up with a slight positive charge. That positive end is then attracted to the negative end of a totally different molecule nearby. Just to give you a sense of scale, a hydrogen bond is about 20 times weaker than a strong covalent bond. So we're not talking about superglue here. Think of it more like Velcro or static cling. A single connection isn't very strong, but when you get millions of them working together, they become incredibly powerful. And to prove how powerful they are, let me ask you a question that seems simple, but has a really profound answer that's rooted in this weak bond. Why on earth does ice float on water? The answer is hydrogen bonds. As water freezes, these bonds grab onto the water molecules and lock them into this really neat, organized crystal structure. And that structure actually takes up more space than when the molecules are all jumbled up in liquid water. So ice is less dense. Without this little quirk, lakes and oceans would freeze from the bottom up, and life as we know it probably wouldn't exist. And at last, we get to the very weakest of them all, van der Waals forces. These things are so fleeting, so temporary. They happen just because electrons are always randomly moving around. For just a split second, more electrons might be on one side of a molecule than the other, creating a tiny, temporary charge that can attract another molecule. It's kind of like the slight stickiness you feel in plastic wrap. By itself, one of these forces is basically nothing. It's almost insignificant. But when you get millions and millions and millions of them all working together at the same time, you can get some truly mind-blowing results. You get a gecko, seemingly defying gravity, walking straight up a glass wall. Phew, okay, so let's put this all together. We're going to create a clear ranking, a hierarchy of strength, because understanding this hierarchy really helps explain why different materials have the properties they do. Looking at this chart, you can see how these analogies just make it all click. At the top, you have ionic bonds, which are like trying to break a pair of handcuffs, incredibly strong. Covalent bonds are like cutting through a thick rope. Metallic bonds are a strong but flexible chain link fence. And then we get to our gentler forces. Hydrogen bonds are like pulling apart Velcro, and at the very bottom, van der Waals forces are like separating two pieces of static cling. But this isn't just some abstract science lesson, right? These bombs are at work all around you, every single day, often in the most surprising and ordinary ways. Here's a great little mystery for you. The lead in your pencil is actually graphite, which is just made of carbon atoms. A diamond is also just made of carbon atoms. But you can write with a pencil, and you sure can't write with a diamond. So what is going on there? It all comes down to a perfect team-up of strong and weak bonds. See, in graphite, the carbon atoms form these super strong sheets, all connected with powerful covalent bonds. But the sheets themselves are only held together by those incredibly weak van der Waals forces. So as you drag the pencil across the paper, you're literally just sliding off those weak layers one by one. One more for you, this one's straight from your kitchen. How does heating an egg turn that clear, runny egg white into an opaque solid? It's not magic, it's pure chemistry. The heat actually breaks all those weak hydrogen bonds that keep the egg's proteins neatly folded. Once they break, the proteins unravel, tangle up with each other, and form a whole new solid network. So the big takeaway here is this. You aren't just made of atoms. You are a masterpiece of atomic engineering. You're a walking, talking example of all this incredible chemistry in action, held together by a precise combination of all these bonds, the strong ones for structure, the weak ones for flexibility. It's the glue of the universe, and it truly is what makes everything, including us, possible.